So, our speaker today is Alexander Braverman from Brown University, who will be talking about Tamagawa number formula for loop rules.
Okay, so thank you very much for the invitation. What I will be talking about, or maybe I should say what I will be talking about towards the end of this talk, because in the beginning I was just reviewing some stuff which has been known for many years, is based on the joint work with D.Kazhdan. And in fact, I should say that this is all a part of the of some kind of ongoing project on trying to create a theory of automorphic forms for infinite dimensional groups. Unfortunately, most of this project is somehow, I think, not suitable for a colloquium talk, so I try to find some kind of piece in this theory, well, in kind of, I should say, theorem construction, which can be presented in colloquiums, which somehow at least partly can appeal to a general audience. We'll see how, if I succeed in doing this. And I should say that this project is joined with also some other people, including Finkelberg, Garland, but probably some others. Okay, so, but like I said, that I'm going to start by reviewing various aspects of the usual Tamagawa number formula, and somehow I think I'd like to divide, well, the board is naturally divided into two parts here, so somehow let me follow this division, and so Tamagawa number formula can be looked at from basically two different perspectives, and one perspective is sort of number-theoretic, so this will be our number theory board, and this will be our algebraic geometry or even topology. So what I'm going to start with, I'm going to formulate on each board, I'm going to sort of write a theorem on each board. And these two theorems will, if you see it for the first time, the theorems will look pretty different. And then the next thing I'll try to do is to sort of match these two theorems to explain that in some sense this is just the same, this is more or less the same theorem, or at least both can be put into a larger framework where, and largely unified framework. So here I'm going to start with some kind of, well, with a certain formulation, and then later we'll need to upgrade it a little bit. But let me first start with the simplest possible one. So the thing that I need to fix here is, well, the common notation of the group G, which is I want to assume, well, that it's a semi-simple interconnected group, but you can think about G being, for example, the special limit group, or you can think about the symplectic group. Or anything like this. So somehow the group S allowed will be perfectly fine for the whole. But in principle, everything applies. Everything works in this generality. And this Tamagawa number, I mean, the question about Tamagawa number, which I'm going to define in a moment, was actually raised by Andre Bale, but in this kind of slightly different language than I'm going to formulate right now. So the question is the following. So let's consider this group over real numbers. So consider, for example, SLN over R. And inside it has a discrete subgroup, which is G of Z, which is discrete subgroup. And then it is known and not difficult that if you consider the quotient, well, this is some manifold, and this manifold has finite volume. With respect to some choice of power measure. See, right here, power measure 1. I should maybe mention that when the group is SL2, then this quotient is closely related with one parameter of a half plane. And then, moreover, of course, this power measure is defined equal to scalar, but basically you can fix this scalar. So power measure is basically given by a top degree differential form on this group, and you can require this differential form as integral. And then, so there's a natural normalization of the power measure by requiring it to be integral, by requiring the differential form to be integral. So the question, first of all, is what is the volume of this quotient under this natural normalization of the power measure. Now here, so let me give you the answer here, and then I'm going to pass the board and describe the seemingly different problem, but then the next definition. And the theorem, which is generalized due to Langlands, I think it's around 1967, is that the volume is equal to the product of the values of the Riemann zeta function at certain integers. So here, let me explain the notation. The notation is the following. First of all, L is the rank G, which is a well, Braverman is defined as the dimension of the Kac-Moody subgroup, and for example, if G is SLN, that's one thing. Now, what are these numbers? G1 up to L. These are certain numbers. So first of all, again, let me say that for SLN, these numbers are the numbers just 2, 3 up to n. So we get n minus 1 of them. In general, these numbers are defined in the following way. So if we consider the Lie algebra of G, we will use it sometime. So if G is the Lie algebra of G, then we consider polynomial functions in this Lie algebra, it's a symmetric algebra of the dual vector space, and we take functions which are invariant under the edge reduction. And it is known that this is a commutative algebra, but it's graded because the symmetric algebra is graded. And it's known that this thing is actually a polynomial algebra of some generators, and there are altogether L of them, and so GI degree.
So these are the exponents.
I think the exponents are these numbers minus 1. So, well, this is some nice formulas. Unfortunately, I don't really have time to explain why this formula is important. So, the Langlands formula was really was really very important because somehow, in the theory of automorphic forms, you need to know some kind of information like this when you deal with such things as trace formulas and other similar construction theory of automorphic forms. Somehow you need to know these volumes, and in fact you need to know these volumes even for a little bit more general setting. But let me. Well, I should have said that. Let me just, for the sake of being rigorous, let me just say it's what's called a split group. That's again, if you don't know what split is, then ignore this. So again, the group SLN splits. Okay, so this is now. I should warn that later we'll need to upgrade this later will need to reformulate it basically. Formulate this in what I call idyllic language, but I'll explain it later. But just, you know, we're going to have a fancier formulation, the same result. Okay, but for now, for the following 5 minutes, let's just completely forget about this. Now let me talk about a completely different problem, but then I want to explain that that's actually in the right. If you look at it from the right point of view, that's really the same. So, okay, now let's do the same, but now, well, G will be the same thing, except that now I want to consider it over complex numbers, and that also X be a smooth projective curve. Complex numbers, so for example, you can take just projective line, or you can take any elliptic curve, or you can take any curve hygienist. So in other words, that's you can think about it as a Riemann surface, but somehow what I'm going to say now, complex structure in this thing will be essential. And then let one G of X denote the space of the modular space of G bundles over X. So either algebraic or holomorphic, that's the same thing here. So again, if G is SLM, that's the same as, this is the same as vector bundles over M. Bundles, let me call them, F of E M with trivial definition such that the top exterior power of this bundle is identified with trivial. Well, one thing I want to, one word I want to say is that this word space here is a little bit delicate. So, so for the expert in the audience, I want to say that I consider this just first of all bundles. There's no restrictions, no stability condition. This is actually, and this thing is actually is an algebraic step. But let's me ignore this question. That this claim is that this is some kind of object in algebraic geometry which parameterizes all principal bundles. And then the question is, what is the homology of the space? Well, let's say it's a complex coefficient, but this is a rational coefficient, the same thing. So this question was essentially started by Atiyah-Bott, although in a slightly different language and actually in a slightly less general context. But essentially the answer was given by Atiyah-Bott, and let me describe that. So first of all, my first claim is that actually the question, this question, well, let me call it question 1, and let me call this question 2. And so my first goal, before I actually explain our work, will be to later explain why this is actually the same question. Or again, the same, of course, it's not literally the same question, but it means that there's a kind of big intersection between the questions. So once again, we're going to put them in a slightly bigger framework, and then so both the discussions would become part of something bigger. Okay, let me produce the answer. So somehow this answer will kind of see, there will be no zeta function here. So this is, I should agree with this as the Riemann zeta function. And let me explain the answer. answer is the following. So we'll continue from here to write in the following way. So let V be a graded vector space. With basis C1, CL is, well, I mean, Deliberate use the same notation as over there, and the only thing is that I want to double the degree, so the degree of Ci is 2 twice and then the answer is the following, that the cohomology of this vector space is equal to the symmetric algebra. Well, let me write it and then I'll explain the normalization times the homology. Well, and the way I'm thinking about homology of X is that I want to think about this as being dual to cohomology. So X is essentially a Riemann surface. So it's a compact Riemann surface. So it's cohomology at least in degrees 0, 1, and 2. And so I want the homology to lead in degrees 0, minus 1, minus 2. Basically, I want H minus I of X. C is dual. This is just another convenient. One remark about this is that you might know that this space is infinite dimensional. And this actually has to do with the fact that this is really not a manifold, but this is something like what is called an algebraic stack, and such things are allowed to have infinite dimensional cohomology. So I should say that the way Atiyah-Bott started this is that usually the way you can think about the typical algebraic stack, you can think about it, just a side remark, the typical example of an algebraic stack is, say, quotient of a point by some group, for example, this group. This is an algebraic stack. And then its cohomology is by definition a covariant homology of a point. And this is sort of the language that was used in Atiyah-Bott, so you can actually think about this model space also as a quotient of some actual space by means of some group. And this is how Atiyah-Bott said it. Okay, now let me say the following, so I'll probably erase this thing. So let me explain two goals I have in this talk. Goals of the talk is first explain the connection between two questions. And second, explain the generalization of this. In fact, I only know a generalization of something like 1 out of 2, but basically explain the generalization to some infinite dimensional setting. In the case when G is replaced by some infinite dimensional group, which is a formal group. So consider just, for example, if you think about the group SLN, that means that it basically consists of matrices with determinant 1. And so here we consider matrices, we would consider matrices whose entries are Laurent power series. So this is formal. Okay. Any questions? I want to maybe make one remark about this. So here, well, this statement is somehow not trivial, but it is actually very simple. I'm not going to explain that, but it's actually very simple to construct a map from the right to the left. Somehow the construction of that map is really kind of absolutely standard, and then kind of the non-trivial part of the appearance to prove that this map is an isomorphic. Here, at least the way this is computed by Langlands, it's really, maybe I want to mention it because somehow I might need this later, is that here the proof of Langlands is absolutely is absolutely not conceptual. The space is somehow, Langlands proof is actually, I would say, quite miraculous. So the structure of Langlands proof is the following. First, this is basically 3 steps. So first, interpret the volume in terms of a certain function, in terms of certain analytic behavior of certain functions on this quotient. Interpret the volume in terms of certain functions which are called Eisenstein series. Certain Eisenstein series. Then part 2 is, so Langlands somehow, one of the earlier work in fact of Langlands on automorphic form was actually to develop some theory of those Eisenstein series, whatever they are. And so use the theory of Eisenstein series to get some formula for the volume. Eisenstein series, and this is generalized developed also by Langlands. You get the some quotable formula. But the quotable formula, it will have some kind of right feature, namely, it will involve values of the zeta function, but it's considerably more complicated than this one somehow. There will be some, first of all, there will be fractions, well, it will be really some kind of bad formula. And then use some kind of combinatorial miracle to show that the bad formula is actually equal to the good formula. And then a miracle happens. Sorry? And then a miracle happens. Well, yes, I mean, in some sense, technically, this part 3 is the easiest one, because it reproduces some combinatorics, but somehow it's combinatorics kind of absolutely strange. It's just combinatorial miracle to show that that formula is equal to good formula. So, of course,
how did this kind of statement? Did he believe this theorem before he did the manipulation, or did it come out?
Yes, so this is actually a special case of some conjecture continuity, but I probably.
Also, when it was computed by Ziegler, by Kac-Moody Ziegler, right?
Yes, and I think that they computed this called classical groups, and then. There is a different way to formulate this, which might seem a little bit more natural, but I still want to stick to this one because it's kind of more relevant to what, because I want to find connection to.
So what happens in this formula in case as a 2D in the classical case?
Just you get zeta of 2, which is pi squared over 6. Well, except that the normalization of the measure which is here, so now if you think about the upper half plane, which is the quotient of this by SO2. Then on the upper half plane, usually the way you tend to write the measure is something like this, and that's not the same normalization. So the volume with like this, I think it's pi over 3 not pi squared over 6, and I can actually explain why it's. So, I mean, here I said that normalization is such to use differential form, and this one, this does not come from there, so somehow you can. But
is it an exercise in this case?
It is. Well, it is more. Well, it's an exercise. I mean, so first of all, we can actually show what is really an exercise is how this form, what is the difference between this form and the form that comes from here, and then with respect to this form, the exercise becomes that you consider the quotient of upper half of base of the zeta, one is equal to pi over 3. I think.
What it has to do with theta?
Because I said that with the right normalization, with pi squared over 6, which is equal to 3.
So the normalization of the body form, how is that related to the one that you would get from the Kelly form? Is it just that, or do you have sort of natural?
Well, I mean, it's not exactly. It probably differs by some integer, so it's not exact. No, first of all, I can't really use the Kelly form here because it's not a compact group. So the Kelly form here does not give you a Riemann matrix. It's not positive definite.
That's okay. Indefinite metrics, as long as they're non-degenerate, still have a long form associated.
Yes, okay, right. So I think that it will differ by some number, which is something like Coxter numbers. So Pressel n will probably differ by multiplication by n. Well, I mean, I'm not completely sure about what I'm saying here, but it's easy to compute. I mean, just the ones that use a differential form, you use an invariant differential form, that's the same as a kind of element of exterior power of the algebra. And you want that to be integral. So it's easy to compare. Okay, so I think I'll probably need to speed up a little bit. So let me. So I still want to explain the connection, and then we'll talk a little bit about the proofs. So as I said, to explain the connection, I need to upgrade this thing a little bit. So let me just completely erase this, and I'm going to put this into some somewhat bigger perspective. So now, one thing that we're going to fix is what's called global field. We fix F. Global field, and global field by definition are having two types of global fields. So we've known that the global field can be either number field, which is the same as a finite extension of U. So for example, the rational numbers will give you a number field. And another source for global fields is a field of rational functions on a smooth projective curve X, but this time over F2, which is a finite field. So, of course, you can reformulate this in the following way. It's the same as a finite extension of the field of just rational functions in one variable, but with coefficients in a finite field. So it's kind of known, the number theory, that this the cases are very parallel to each other. I mean, this case is usually easier for many purposes. But somehow the general structure is similar. And then one thing you can do for those fields is the following. So given this F, you can look at various local completions of this field, or various norms on this field, and various local completion. So suppose that we embed F into some local completion, which is known by Fp, so P just runs over a set of parametrizes different norms on this field. So for example, here, what kind of local completion can we talk about for Q? So for Q, we can either talk about the field of periodic numbers, or we can talk about real numbers. And in this case, well, let me talk about this case. So what we can do is that we can talk about using some point of the curve, and then we can embed this rational functions into. So if we fix, say, Z, which is a local coordinate near this point, then we can embed this into the field of Laurent power series with respect to this local coordinates. And then, so for every such completion, this is locally compact field, and I'll mostly be actually talking about this case because this is the one which is more related to geometry. So, for example, we see that over there we have a smooth projective curve, and now we also have a smooth projective curve, except that there's all complex numbers here, so a finite field. But it's clear that it doesn't really matter. And the next thing we form is the ring of adeles, which is what is called the restricted product of all this B prime means restricted product, and restricted means the following. So in almost all cases here, so here it's always the case, here it's the case always except one case when we have real numbers. This is what is called the non-Archimedean local field, so it has some kind of, it's totally, as you can, topologically it's totally disconnected, and it has a maximal compact subring, which in this case is ZP, and in this case it is the ring of Taylor series. And in general, I'm going to denote it by OP, And so this means we can say the product of, well, it's an infinite product. So here, for example, we'll make product of all primes times one more element. But the requirement is that almost everywhere the element is in OP. And then the true theory of automorphic forms is really about the following. So we can consider, so this A, this is a locally complex ring. And inside this ring, we have our field F, because somehow F sits inside Fp, and it's kind of it's easy to see that it actually embeds into adeles, and since there's discretes of P. So the actual quotient, which is important for number-theoretic purposes, is actually this one. So this is a locally complex group, and this is a discrete subgroup. So so I want to look at this quotient. Let me go.
So almost everywhere is presumably not in the measure theory sense. What do you mean?
No, almost everywhere means everywhere except finite many places. Yes. So there's no measurements. So, for example, here it will mean almost every prime. And so the statement that Q embeds in the adeles is the statement that if you have a rational number, it's Q sits inside QP, but for any given rational number, it lands inside CP for almost every P. And so let me call this, let's look at this quotient. And so in the case when the field is Q, this quotient is somehow closely related to just G of R and G of Z. I'm not going to explain exactly what the relation is, but somehow, but that close to related. And so let us put a higher measure, let us choose a higher measure, on GA. So to put the measure on J, so it's easy to see that just the same as to choose a measure on G of Fp for every P. So such that the volume of G of OP is equal to 1 for all. So this doesn't really define everything in this case, but somehow it describes our completely in this case, because in this case somehow we will also need to say what happens at the real point. But let me just ignore this. In fact, the real point you have to normalize in exactly the same way I described before. And then the question is, what is the volume of G of A and G of F? And the claim is that in the case when...
So, sorry, starting with you, so G is the original semi-simple.
Yes, but now I need to, but I assume that it's defined over, well, say over this field or over images, basically. So just, in fact, I said this word split, so let's think about grouping G being just SLM. So now, like I said, just SLM, so it means that, actually, this thing is a ring, I consider there are matrices with values in this ring, quotient by matrices with values. Okay. So this is the question, and now the answer is almost the same as before. So from now on, just to simplify the discussion, let me switch really to this case. This is called a case of functional fields, and everything can be actually said to non-fields as well, but it will be just simple for me to describe it as a functional field. And then the statement is the following, that the volume, the same calculation of Langlands actually shows that the volume is equal to the following thing. So this is a theorem. Yeah, well known theorem. So, well, let me write the notation, and then let me write and explain the notation. There's some kind of simple factor here. And which I'll explain in a moment. Then there's a product of all time from L. So zeta F is the following. So for every such global field, one can associate certain zeta function to F. One associates zeta function. And such that in the case when F is the field of rational numbers, this is a Riemann zeta function. If it's any number field, then this thing is called dedicated zeta function. And in general, so for every global field, you can define certain zeta function, which behaves in a very similar way to the Riemann zeta function. And so I'm not going to again give a definition, but somehow since zeta is equal to zeta Riemann. But there is a construction of this thing for him. And this is the zeta function.
And again, what is d sub I?
D sub I are the degrees of generated invariant polynomials, so somehow for SLM this would be just numbers 2, 3, up to n. And G and little g is the genus of X. But, you know, this is just a normalization factor, which you know it can do. Want to write this precise. Now let me maybe spend another 5 minutes to explain the relation between this two things, and I'll talk about the loop case.
What's Q?
Q is this Q. We're working on finite. So there's some normalization factor here, which we can also write it for a number field. In fact, when number field is Q, which well, field of rational numbers, it turns out to be 1. Otherwise, it has to do with discriminant of the field.
Is any of these things the Tamagawa number?
I'm sorry?
In your title, you had Tamagawa number?
Well, this is the Tamagawa number. And this volume is the Tamagawa number. Okay, so now the connection between these two things. So the connection is, of course, the connection we not absolutely direct because here we're talking about the curve over complex numbers. There we're talking about the curve over finite field. But as I said, let's pretend that these are the same things. And then I need to recall the following general construction of Braverman, which says that suppose that Z is some algebraic, let's say first algebraic variety over finite field. Then Braverman defines certain cohomology theory, which is some Vital cohomology, which behaves very similar to usual cohomology of complex numbers. And this cohomology is with coefficient in the field in the field of quadratic numbers, where L is different from the characteristic. Q, basically, this Q is the power of prime, so it should be different from. And so, what Braverman showed is that this was actually one of the main reasons why this theory was developed, is that the number of points described over finite field, which is just a finite integer, is equal to the whole length. So you can see that this cohomology. So alternating sum, and then this cohomology actually comes with a certain automorphism, which is called the Frobenius automorphism. And then we should consider the trace of this Frobenius automorphism on ith cohomology. In fact, I need to put, to be completely precise, I need to put subscript C here, which means cohomology of subscript C. And more generally, if Z is a stack, then you don't need to know what a stack is. The only thing that so the way you should think about stacks is that it's the same as a variety, but every point has some kind of group attached to it, which is some kind of automorphism group of this point. And then instead of writing the number of points, what we should do is that we should sum over all points of this thing, and we should take 1 over a number of elements in the automorphism group of this. And so if there are no automorphisms, then we just count every point with weight 1, otherwise we just how to do it this way, and this is then do the same form. And the last thing that I will say about this is that how to relate these two things. This is actually comes from the following observation of, which I guess is also due to Taylor.
So, interpreted is some kind of legend.
Yes, this is exactly like this one. So, this is an observation by Taylor that if one considers, in the case of functional fields, if one considers this quotient, which I considered before, GOF, but also here take quotient by integral adeles, which means that we put this in this ring O at every place. This is exactly 1G of X over X is 17 points. And this isomorphism is somehow smarter than you may think, because here I said that bundles have isomorphisms, and here we can see some kind of double quotient. And points in double quotient also have isomorphism, because the action of this group on this quotient is not free. And so the automorphisms also match. So this is an isomorphism which sort of also respects automorphisms. So therefore, our volume, so the corollary of this, which you can easily get from this, is that the Tamagawa number, which is our volume, is just equal to the following. This is the corollary. Volume of GK. This is equal to summation over all f equal to g of x, 1 over number of elements in the automorphism. This is working on a finite field. It's easy to see that the automorphism group of every one is finite. This is an infinite sum, but the thing is that this infinite sum is convergent. And because of what I explained here, it can be interpreted in terms of cohomology, and then you have to do the same calculation criterion for the finite field. And you also have to take the actual Frobenius into account. And if you do this, then, you can actually formulate an analog of this theorem in the Levy cohomology of a finite field. And if you do this, then you get the same formula of Langlands with probability value. So just write this. So an analog of Atiyah-Bott calculation exists over FU. And again, it's sort of, in this case, we need to know not only the beta number, but also we need to know how this Frobenius isomorphism, whatever it is, has. But somehow it can all be done, and then when you take trace of Frobenius, then trace of Frobenius, we get the Tamagawa number. So this argument, of course, works only when we talk about this functional global field. So for rational numbers, it's not going to work. So for rational numbers, we still have to. This gives basically conceptual proof of the Tamagawa number formula in this case. For rational numbers, you cannot do this. Somehow you really have to sort of go through this Langlands calculation. There's basically no other proof available. But in this case, somehow you get some sort of conceptual proof. It's conceptual because, like I said, this isomorphism, at least the map in one direction, so we can define in a very conceptual way. And so from this point of view, this is really the same formula. So somehow, at least if you upgrade this formula to calculation of geometric cohomology or finite field, that really becomes the same. Okay, so this was the review of finite dimensional story. Any questions before we switch to groups? So of course, when we talk about groups, I won't be able to say anything really intelligent. I'm just going to later we fit it with some formulas, but I think that those formulas are actually nice. And what I want to stress here again is that this calculation is kind of conceptual, and the original calculation of Langlands is really sort of based on some pretty complicated procedure. But in fact, in the group case, that's exactly what we're going to do, because I don't know the right analog of this in the loop groups, but I do know the right analog of this thing. Okay.
Would you motivate why you should go to the infinite dimensional case?
I'm sorry?
Would you motivate why should you go to the infinite
well, somehow, like I said, this is really part of some theory of, in the finite dimensional case, this is really part of some theory of automorphic forms, finite dimensional G. And I mentioned in the beginning that this is all a part of some big project of creating theory of automorphic forms for infinite dimensional groups. And why we want to do this is, well, the simple answer is that it seems like it is partially we can do this, and somehow in saying in representation theory for many years now, like for the last maybe 25, 30 years, it was known that somehow it is actually interesting for many purposes to generalize some things about finite dimensional semi-simple groups to loop groups. And somehow they, from a certain point of view, they behave similarly, but not exactly similarly. And also there are some very concrete applications. If this theory really exists, which is not completely clear now, then actually I do have some very concrete applications in mind. Concrete applications for just theory of usual automorphic forms. But I don't think I can explain this. There are very strong reasons to desire to have this theory of automorphic forms and Langlands conjectures and so on for infinite dimensional groups. Even if you want to prove things only for finite dimensional groups, somehow having more groups into the in the game somehow will be extremely beneficial. But to explain this, I'll really have to get into some technical. Okay, now G goes to the V group. Now, of course, the first question I should ask here is whether you can define it or not. But that's not how we're going to proceed. The first question we're going to ask whether we can guess the answer, and then the next question will be: can we define the question? Can we formulate the question so that the answer will be exactly that one? So can we guess? And this was actually one of the main reasons why I brought this theorem into account, because actually if you look at this thing, then from here we can actually very easily guess what kind of answer we want. And the reason is that, if we want to describe, for example, this cohomology, forget whether we can define it, but let's think, can we make sense of the right-hand side of the loop group? Well, the only thing we need to say is what is this, well, let me call this VG. And the question is, can we make sense of this VG for a loop? And this VG has the property that it's symmetrical to VG. This is exactly the invariant homology. Now we're going to get a little bit more technical than before. And now we can take the invariant homology of point with respect to the loop group, just to actually define. And you wonder whether this is actually symmetric, whether this is isomorphic to symmetric algebra of some vector space.
So is that expression over there really secretly supposed to be some equivariant cohomology or model of the equivariant cohomology?
You mean which expression? This one. You can do this except that this is invariant homology affects some infinite dimensional group, affects some infinite dimensional space, affects some infinite dimensional group.
So I see, on the other side, so there's some model of equivariant cohomology, you change the differential.
No, it's not. I can explain it later. To construct this map is really very easy. Just you have a universal bundle. This is just kind of use the Chern classes of the universal bundle on bunch E times X. Well, let me say this later. I mean, this is, to construct a map in one direction is really very easy. But what I want to say is that this is really, this is isomorphic to some symmetrical or some vector space, except you have to be a little bit careful that this vector space now is going to have both even and odd generators. And then what I mean by symmetric algebra is that when you have a graded vector space, then it should be somehow symmetric algebra in the even direction and exterior algebra in the odd direction. And I can describe what the space is. So what the space is V of G E. It turns out to be just G tensor the cohomology of the group itself. And this is actually an exterior algebra on some generators, variable in A1 up to AL, where the degree of AI is equal to 2DI minus 2. So therefore, okay, let me first pose a question to which I actually don't know the answer. So now,
it's a compact form of
No, I'm only working with complex groups. Algebra, everything is algebraic. No. So this way, somehow, this vector space is defined, so the right-hand side of this expression is defined. So the question which I don't know the answer is, can one define an analog homology of function of x? Can one define it, say it like this? Can one define just h star from g of t x such that So this is something I don't know how to do. And the problem is that somehow when you try to do this thing, that somehow things, the spaces you have to work with become two and dimensional, and I personally get just scared. So maybe it's just a psychological problem, but I don't know how to overcome a psychological problem. Somehow on the other hand, what you can do is the following. So you can assume that you can do this, and then you play this game with taking trace of Frobenius and so on, and then we can guess the answer to the Tamagawa number. So then use this as a kind of guiding principle, and again, let's try to define the right-hand side of the Tamagawa number formula, and then actually the next question will be whether we can define Tamagawa number. So what should be the right-hand side of Tamagawa number formula? Well, let me first write a slightly wrong answer. Slightly wrong answer is really what happens when we take trace of Frobenius in this thing. And what it will become, become product over all I from 1 to L, zeta of di over product from I from 1 to L, zeta of di minus 1. And think about this coming from this even generators, and this coming from the odd generator. However, okay, so you might want to get this answer, but there's actually a problem with this answer. And the problem with this answer is that the first of these numbers, di, is the smallest one, which is always for any group equal to 2. And for this, there is clearly a problem because the zeta function, so I said that this zeta function behaves similar to the Riemann zeta function, so particularly has a pole at 1. And therefore, you're basically dividing by infinity here, so this number is actually 0. Formula is a 0 number. So this is a formula. But the reason for this is that this formula is actually smarter than, at least it's smarter than I was at the beginning when I was looking at this. And the reason is the following, that it is known in the theory of loop groups that the loop group is actually a bad object. A good object is the sample extension of a loop. So this loop group has a natural sample extension. If it has natural sample extension, which I would be called G-hat. So it feeds into short that sequence like this, and here it's a sample extension by means of the multiplicative group, so of whatever field we're working with. So if I'm working with this field cap, here. Actually, so it's known that this group is much better than this group. For example, for representation theory purposes and for many other purposes, this group is much better. So somehow, now let me formulate the theorem. Unfortunately, I can't really formulate the theorem precisely, but the theorem says the following. That one can define this is our joint theorem. First, there is a definition which is really quite technical, and I can't really formulate this definition here, but one can define the Tamagawa number for G hat. This is part 1 of the theorem. Part 2 of the theorem is that this number is equal to this product of zeta of Zi from 1 to L over product of I from 2 to L zeta of Di. So somehow we have really killed this singular thing, and what kills the singular thing is exactly sample extension. This is how it happens. So let me finish by making the following comment, that both the construction, the definition of this number, and this calculation are pretty horrible. So, and it's really, it's done by mimicking this work of Langlands, but so somehow what so Kazhdan and I we have developed some theory of, and also based on some early works of Garland, developed some theory of Eisenstein series. And then one can give a definition. So this definition one can give. So one can give a definition and give a definition of volume such that at least some version of this Langlands interpretation of the Eisenstein series and interpret it in terms of Eisenstein series. And then the next thing is that by doing something similar to, but it's a little bit more complicated than what Langlands did. So 1. Then 2 is that use the theory of Eisenstein series to get a, well, let me say a really horrible answer. So horrible answer, but involving the values of the zeta function. And then use, again, a combinatorial miracle, but this time the combinatorial miracle is going to be considerably more complicated, considerably more miraculous, I would say. Than, so in fact, I should say that when I first got this answer, I was absolutely sure that it cannot be anything close to this one. But use some very strange combinatorial miracle. It is very strange for me. Combinatorial miracle. So this is, and again, I mean, the definition is really technical, so I can't explain it, but it sounds like I don't even want to explain it because I'm not sure. I mean, this definition, I'm sure it's formally correct because it gives the right formula. But really, I'm sure it should be a better definition, but I don't know what this better definition would be. And the real question for me would be to sort of define cohomology of the space in some kind of natural way, and then really prove that it's isomorphic to whatever she is. But this is something I don't know how to do. But really, I should say that this is all an application of the theory of Einstein series. The theory of Einstein series is somehow, I think, quite non-trivial. So somehow the fact that from there I get the right formula, for me, it serves as an indication that the theory of Einstein series in the infinite dimensional setting is kind of correct, because it's the right generalization of the usual theory of Einstein series of finite.
So you mentioned several times that there's this key step one in interpreting the volume in terms of Eisenstein series. Can you just say how that goes in the finite dimensional case? What is it you're using about Eisenstein series?
Okay, what you're using is the following. Well, let me try. So first of
You
all,
have to give a complete explanation. But
well, I mean, first of all, you write some particular Eisenstein series, actually the simplest possible Eisenstein series. And this Eisenstein series, it doesn't matter how it's defined. It's actually a family of. It's a function on this quotient, or this adele quotient. So you write some EUPADs, which is some actually family of functions. So it depends. For SL2, S will be just a complex number. For higher groups, will live in the complex Cartesian subalgebra. So this is some family of functions. On this GOK. And then this family of functions has the following property that it has a pole that's at a certain point. So the fact is S lies in the dual space of the Cartesian subalgebra and has a pole and some normalization at some particular point, which is called rho.
So more of it is trying to define some function on the maximal torus?
No, it's not the maximal torus. It's just a family of functions here, which you write by some explicit formula.
It's a conjugation variant?
No, it's a function on this quotient. Okay. So for SL2, it's the, well, if I, instead of use SL2R or SL2Z, then the way it can be written in the following, just you can think about this as a space of lattices lambda in R2. And then what you take the function norm to the power S and sum it over the points of the lattice. More precisely, you sum it over primitive points of the lattice. So you see the summation over lambda primitive elements. And then actually very fun with this. This is EOS value. We can write it in this generalizer about prime G and prime global field. Write this in expression. And then there's a point where it has a pole, like the first order. And then we take the residue, and this residue turns out to be a constant function. And then, because of the definition of Einstein series, to integrate this residue is very easy. Somehow we can get some very, very easy, much easier than this formula for the residue. And then we actually use this quite complicated theory of Einstein series to actually compute what this residue is. So for some very abstract reasons, you know that this residue is equal to a constant function, but then you need to compute what this constant rate really is. And this, for example, this values of the zeta function of Ti is they appear when you compute this constant.
So what's the relation of the residue to the volume?
No, you want to integrate, volume is the integral function of 1. Instead of integrating function of 1, we're going to integrate the residue. And I claim that for reasons which, I can't explain now, but it's really simple. Integrating this residue is very easy. So you can get some simple formula for integral of the residue, and it will have nothing to do with, this di's will not appear here, for example. Somehow it gets a very simple formula. And, but then, so therefore, because this is a constant function, means that its integral is equal to the volume times actually this constant. And then the next thing is to compute this constant. And when we compute this constant, there's really somehow, there's some computation which, so the point is that lambda is actually also starts to some degree called the constant form of finite series, and the constant form of finite series is written explicitly in terms of certain L functions, which in this case will be just the zeta function, and then you look at the, well, there's some technique how we compute this, how we should compute this rest. So this is, I mean, I'm not sure this is the answer, but the procedure is that instead of integrating function 1, you integrate some other function, which is actually secretly a constant function. But that's kind of another thing here. But this other function is very easy to integrate by construction. And then you say that this function is constant, and we actually compute this constant by using some kind of very complicated procedure. And so some theoretic analog of this argument turns out to work in the infinite dimensional setting, but there, actually, the first step is more or less used as a definition. I mean, combination. Okay, well, I cannot say this, but you can, by looking at this thing, you can actually hook up a definition of this volume, and then somehow, like I said, the combinatorial relation of this integral and the proof that it's equal to this, it becomes really some kind of huge combinatorial mess. But somehow it's, so the fact that it works is kind of, in some sense, very miraculous. So it's based on a lot of combinatorial identities. For example, it's this Macdonald conjectures is one of the things which you use in the proof of this form.
In the affine case?
In the affine case.
Do these data functions, these are, I guess, associated with what the field functions on the. This is all out in the field functions.
I mean, okay, so this should work for any global field. At the moment, I can do this rigorously only for functional fields. I don't know how to do it rigorously for them. And there is some abstraction there, which I don't want to talk about, but there's a serious abstraction for functional fields. But, so for functional fields, I can, first of all, I mean, the abstraction is in the definition, so I don't know the definition for somehow in a number of cases. So for functional fields, the claim is that first of all, you can define the volume rigorously, and then you can compute it and get this.
Is there some relationship between zeta of pi and zeta of pi minus 1?
Well, I mean, no, I mean, it's, and you already know it, but see, this question is kind of misleadingly complicated, because if you look, for example, in SLM case, I said that the di's, I mean, this is actually, for SLM, for example, this expression will be very simple, because the di's are just numbers 2, 3, up to n. So what you're going to get here will be really just, I guess you'll be just left with 0 of n. But, you know, for other groups somehow you don't have, I mean, for every group you can select, I mean, you always get some cancellations, of course, but somehow it won't be that drastic, but somehow, in some sense, the right way to write, to present the form, I think, is this one. So the fact that somehow I have some cancellations here is kind of, in some sense, irrelevant. And again, somehow, the point that I want to stress is that you can guess this formula by guessing what the cohomology should be. But I don't know how to define cohomology so that it would be literally look at this.
You sure don't know what volume is.
I'm sorry?
You sure don't know what volume is in this context.
Well, I mean, I said I know some definition for them, which I don't like, basically, so that's why.
So you calculate total volume, but you don't have a measure actually, so you cannot integrate.
No, actually, it's a little bit different. So there is a measure there, but the problem is that the volume with respect to this measure is infinite. So you actually have to do some renormalization to actually define it. So this Einstein series they used in order to also renormalize this infinity. So I mean, defining a measure is non-trivial, but somehow you can do this, and it turns out to be just relatively infinite. And then you have to do some other stuff in order to regularize.
In the five-dimensional case, your Einstein series satisfy some differential equations which we use to integrate at once. Do you have same equations here, like the moving invariant operators for the infinite dimensional case? Because here you still
I think the differential equations are not really. Well, first of all, in a functional field case, there will be no differential.
Right,
the expression will be not differential.
Right, in the global field.
But it will be some. Probably what you mean is that the eigenfunctions of certain commuting operators,
Right,
which is also K algebra. And yes, you can do this, and this is true in the affine case, but somehow this, for some reason, this plays no role here. So, and even in Langlands calculation, this actually the only role it plays in Langlands calculation is that you can use this if you can use, for example, this in order to prove that this residue is constant. Because somehow constant function, because then this residue will be an eigenfunction of the K operators with some prescribed eigenvalues, and then we can show that the only function which is a K eigenfunction with those eigenvalues is a constant function. So that's the only role it plays.
So there's no appearance of the curve, the genus of the curve in this formula?
The genus of the curve is somehow, it's actually absorbed in the definition of the volume, actually. And this is, again, in number theory, it's kind of known that this is what it should do. So now this is about this Tamagawa number, that's a very good survey paper from 1984, I think, by Australia, where somehow there, if you look at his normalization of this Tamagawa measure, then this factor, which involves the genus of the curve, or in number field case will be the discriminant of the field, it's actually absorbed, it's sort of put in the definition of the measure. And so here we're kind of forced to do this because you see this factor was e to the power g minus 1 times the dimension of the group. And the dimension of the group now is infinite. So unless you somehow manage to absorb this factor in the definition of the measure, you have, in some sense, that's the same thing I was talking about before. So that's, this is in some sense why the volume is infinite, but then we can sort of do something basically absorbing this factor into the definition so that it becomes finite.